The video episode we're going to work with today is something that's going to focus on positive ion formation. Whenever forming positive ions, it's of benefit to follow the rule. Whenever making a positive ion, we always want to make sure that we remove electrons of the highest N value or energy level first. For example, let's say we wanted to make a positive ion out of the Na atom. The sodium atom's electron configuration is 1s2, 2s2, 2p6, 3s1. We want to identify what's our highest N value or energy level for any of our electrons. To form the Na1 plus ion, we'll remove one electron from the highest N value. In this circumstance, the highest N value is N equals 3. Right up here, the 3s1 electron. Therefore, we're going to remove the 3s1 electron first to form the Na1 plus ion. The electron configuration we would now see for the Na1 plus ion is lacking the 3s1 electron, which is why we now have a positive 1 charge instead of a neutral atom. So in forming this ion, the 3s1 electron is removed. And the reason we remove the 3s1 electron is that with an N value of 3, that's the highest N value of the electrons we had available, which is why that electron was removed first in the formation of the positive ion. This rule for removal of electrons is of particular use when looking at the positive ion formation for the transition metals, which is in the center of the periodic table, this region, where we first encounter the D sublevel. For example, let's take a look at element number 41, neodymium, which is an example of a transition metal when it goes through the formation of a positive ion. Looking at the electron configuration of neodymium, the shorthand version, it finishes with 5s2, 4d3. A quick glance indicates when we're looking for the highest N value that 5 is our highest N value in the electron configuration for neodymium. Since 5 is the highest N value, therefore N equals 5 electrons are going to leave first when we form a positive ion. The electron configuration for the neodymium 2 plus ion would now look like this, where the N equals 5 electrons have been removed. Since right in here we removed 2 N equals 5 electrons, the 5s2 electrons are now missing. That's why this ion would end up being a positive 2 ion for neodymium. Let's do another example with the element lead. The shorthand for lead, its configuration is 6s2, 5d10, 6p2. Again, let's look for the highest N value electrons. In the lead atom, we can see N equals 6 for the 6s2, and also N equals 6 for the 6p2 are our highest N value. So these electrons are going to be the electrons that leave first. Now the P sublevel is ever so slightly higher in energy than the S sublevel. So when removing these N equals 6 electrons, the 6p, these 2 electrons are going to go first out of the 4 level 6 electrons. With the 2 6p electrons removed and missing, we've now formed a Pb 2 plus ion by removing the N equals 6 sublevel P electrons first. Continuing to remove level 6 electrons, the highest N value, next to go are the 6s2 electrons. With those now removed, we now have a Pb with a 4 plus charge. This would be one reason why we see lead existing in 2 different charged states, where it can be Pb2 plus when only the 6p2 electrons have been removed from N equals 6, and then it becomes Pb4 plus when the 6s2 electrons are also removed. The iron atom illustrates another type of example. Again, we'll look for our highest n value. So here the 4s2 electrons at n equals 4 are going to get removed first. Once the 4s2 electrons are removed, we form an iron with a positive 2 charge. Now we know that iron also exists where it has an ion with a plus 3 charge. We can see all n equals 4, our highest n value electrons have been removed. Once all highest n value electrons are removed, then the next highest here, the 3d sublevel, can have electrons that get removed. And there's a reason why one additional electron is removed from the 3d6 arrangement we see in Fe2+. This is the current arrangement if we do an orbital diagram of the 3d6 sublevel for Fe2+. What's observed to occur is from the 3d6 sublevel, one additional electron is removed, creating, when we look at the molecular orbital diagram for the 3d sublevel, the unique configuration where the d sublevel is half filled. This half filled arrangement is slightly lower in energy than the alternative arrangement, and consequently that's why we form this Fe3+ ion, where the final configuration would have the argon core and then 3d5. For our next topic, in this little video, we're going to take a peek at the orbital diagram for a carbon atom and also for a neon atom. Looking at the carbon atom's atomic orbital diagram, we can see that it has several electrons, here and here a couple electrons, that are unpaired. Whereas neon, all the electrons exist as pairs. This has implications for the behavior of an element. The terms that chemists use to describe this arrangement is if something has one or more unpaired electrons, that particular element is identified as being paramagnetic. If all the electrons in something are paired, that's then known as something that is diamagnetic. Things that are identified as being paramagnetic, containing one or more unpaired electrons, behaviorally, they're going to attract very slightly to a magnetic field. On the other hand, something that's identified as being diamagnetic will repel very slightly in the presence of a magnetic field. This could allow for chemists to identify if the compound in question has all paired electrons or has any unpaired electrons by the behavior in the presence of a magnetic field. Final piece of this video episode is a concept known as isoelectronic. Things that are isoelectronic, they share the exact same electron configuration. For example, the species N3-, O2-, F1- neon atoms, sodium 1+ and magnesium 2+, all share the exact same electron configuration. The electron configuration for all 6 of these species is 1s2, 2s2, 2p6. These we referred to then, these are identified as being all isoelectronic with one another.